Observe the foot of a cyclist spinning at high speed. From the outside, the pedal stroke appears as a mesmerizing blur of perfectly fluid motion. This rotation is an illusion. Underneath that smooth circle, human power delivery is highly irregular, occurring in uneven bursts that waste biological energy. The problem lies at top dead center. On a traditional bike, the crank arms are locked exactly 180 degrees apart. When the pedals reach this vertical alignment, the rider's downward force produces zero forward drive, creating a momentary power vacuum. Every time a rider pushes into that vacuum, they generate wasted energy. Instead of turning the wheel, the force creates micro-decelerations that translate into lateral shockwaves, traveling up the crank and stressing the rider's knees over thousands of revolutions. Standard bicycle drivetrains are designed for the rigid symmetry of metallic pistons, but human legs function as biological levers with specific zones of peak strength and extreme weakness. Early attempts to fix this dead spot, such as the Biopace oval rings of the 1980s, failed because they maximized resistance at the weakest part of the stroke, which increased joint strain. Rotor attempted a different mechanical solution with the RS4X independent crankset, a design that allows the crank arms to move independently. This geometric schematic shows the internal linkage. When the bottom pedal hits the 6 o'clock dead spot, mechanics force the top pedal 15 degrees past vertical. Bypassing the power vacuum maintains forward momentum. This correction increased power 10%, providing relief for knee injuries. However, these gains came with significant practical costs. The complex internal bearings were prone to failure, required specialized maintenance, and added considerable weight to the bicycle. A mechanical solution is only effective if the hardware is durable enough for the daily demands of a rider. Engineers looked for a way to replicate the power boost of an independent linkage without the weight and complexity of moving parts. The Q-ring stretches the circle into an oval with a 1.10 elongation ratio, providing a larger gear for the power stroke. To protect joints, a 0.993 form factor allows the oval to imitate a round ring at the minor axis, preventing jerky transitions. Rotor added individual adjustability through a ring of 35 machined anchorage points. These holes allow riders to rotate the oval peaks to match their specific body geometry, aligning the ring's maximum leverage with the exact point where their muscles are strongest. Biomechanical efficiency depends on hardware that can be tailored to the specific physical measurements of the person riding it. When the gear ratio matches the rider's natural leverage, the muscles no longer have to strain to kick the pedal through the dead spot. This efficiency results in a 4% power increase and a 9% reduction in lactate buildup, as the muscles perform less anaerobic work to maintain rotation. This smoothed-out power delivery also improves traction on loose wheel, is less likely to slip during the sudden bursts of a jerky pedal stroke. We can see the result in this climb. A standard round ring produces pulses of power that can break tire contact, but this oval delivery provides the consistent grip needed to accelerate through dust and gravel. Performance in cycling is optimized when the machine is engineered to accommodate the biological realities of the human frame, rather than forcing the body to conform to a rigid mathematical circle.